Right, good day once more, good people. Today, I would like us to look at the retrosynthesis of simple alcohols, right? So what happens in this case now, like, if I look at my compound, in fact, like, the first thing that I need to do, like, I must set up a key, right? Like, in my key, you see, I say that I need to identify my compound first. So if this is my compound, let me identify this compound. That is in terms of what? Of functional groups. So this is an alcohol. There's my OH group. Right? So this alcohol has got a cyano group. Right? That's my other group that is there. Right? Then my other two groups, I've got a CH3 group here and a CH3 group here. Right? So, how do I carry out a disconnection of an alcohol, right? That is a neighbor that is a what? A cyano group. The rule here states that, right, whenever I have a hydroxyl group, what we call like neighborhood. So where do I need to start, right? I always need to start, or rather, an ideal starting point is where I have this neighboring group, which is in this case my neighboring group is what? Is my CN. That's where I will initiate my disconnection, like so to speak. There's my OH, this OH has a what? A neighbor. So it is here where I need to initiate my what? My disconnection. So remember, with disconnections, right, we imaginarily break down this molecule, which is our target molecule. We break it down into what? Into smaller, what we call like molecular components, into what we refer to as synthons, right? We don't do that like haphazardly. We follow logic, right? Because at the end of the day, we need to be able to reassemble these synthons, to reassemble these smaller molecular what? Components, so as to be able to synthesize, so as to be able to come up with a design in terms of what? Chemical synthesis that will lead us to our desired what? Product, right? In this case, this type of alcohol. So how do we carry this in this case now? So this is what happens here. The bond between your carbon and your carbon-silyl group, right, it gets broken, right? That's what we imagine, right? The breaking down of that bond. Now, if that bond breaks, right, so what are we going to get, right? So we are like moving backwards in this case, right? So we use this type of arrow, right? So what I'm going to be left here with, I will be left with a CH3 here, bonded to carbon, bonded to my methyl group this side, and then there's my oxygen that is bonded to hydrogen, 1, 2, 1, 2. So it means that now like this carbon atom here has lost this pair of electrons, and as such it becomes what? Positive in charge. Then what happens to the CN ion? Then the CN group becomes a cyano group that is with these two what we call like electrons, or this lone pair becomes negative. Now, what then do we see now in this case now, like here, we've got a charge here, a single bond, then immediately thereafter, we've got a source of electrons, right? So, it means that now like here, these will come over here to come and stabilize the charge. So, the lone pair of electrons from this oxygen will come here to form a double bond, right? So, what's going to be our next step in this case now? There we go, right? Then we will end up with CH3 bonded to C, bonded to our methyl group, and a double bond here. Oxygen, only one lone pair remaining, and that oxygen-hydrogen bond. What happens to oxygen here? Oxygen has lost these electrons and therefore becomes positive in charge. Now, if we were to move backwards where did this Cn minus come from? Right? Where did it come from? So we use our what we call like knowledge of chemistry that we studied at first year, at second year, at third year. So it means that like this one, for example, might have come from Na plus Cn minus. You see, this is where this might have come from, right? Now, what happens here now is that now like we end up with oxygen that is positive in charge, right? Oxygen that is positive in charge and oxygen that is more electronegative than hydrogen, and therefore this oxygen will take away the bond pair that it shared with what? With hydrogen, right? And then what do we see now if we move backwards? So it means that now like here we must have started with the C double bond O, 1, 2, 1, 2, bonded to CH3, bonded to CH3. So this is our acetone. The common name here is what? Is acetone. So we have generated what here? Acetone. This must have come from acetone, right? So plus what else here? What happens to that hydrogen? That hydrogen falls off without electrons. Then it becomes H plus, right? Where is this one coming from? We know that even before we show those charges, this must have been NaCN, right? So in a nutshell, now, like this target molecule, this is the retrosynthesis, working the synthesis backwards, right? So in terms of designing a chemical route, a chemical synthetic route, this is what we would do. We would break this then into this molecular, what you call like small molecular components, right? Moving backwards, I come over here. Moving backwards, I come over here. Moving backwards, I come over here. So it means that now, like, once I reach here, then it goes without show that, like, here, I will therefore now, like, say, therefore, my synthesis for the target molecule will look like this. Here, I will have my C double bond O bonded to CH3 bonded to CH3. Then this is how my synthesis is going to look like. What are we adding here? We are adding NaCN. In the presence of what? In the presence of H plus. What will this give us? This will give us our target molecule. This will give us CH3, C, CH3, right? OH, there we go, bonded to what? To Cn, right? So, and this is our target molecule, right? And then I'll show you now, like in the next class, right? In terms of the mechanism now, like you see, how can we reassemble our synthons? How can we reassemble our small molecular components, right? To give rise to our target molecule. I will see you in the next class. Don't fear, don't fear, don't fear. Organic chemistry is easy, organic chemistry is beautiful, organic chemistry is fun, and we need to enjoy this. Thank you.